5-point charges on each of charge plus Q are placed on 5 vertices of a regular hexagon of side 1 or L, side L. Find the magnitude of the resultant force or charge minus Q placed at the center of the hexagon. Okay, hexagon is there and the 5 points charges each on the charge of the plus Q, 5 points. Okay, we'll see the diagram here. See, this is the diagram. Okay, this is a hexagon and on each side it is a plus Q charge is there on first, second, third, fourth and fifth side. But on the sixth side at the center they are going to keep it the minus Q. And in this one, what is the force we need to find here? Okay, now it is a regular hexagon, so all are means equal to 60 degree. Okay, then if I am going to take here this force is acting in this direction. Okay, in this direction. This force is acting in this direction, this force is acting in this direction, and this force is acting in this direction, this force is acting in this direction. That means this is equal. And for this one acting in this direction, then I can write here the force acting on minus Q is equal to F is equal to constant K into Q times Q upon the length, that is length square. And this constant value, if I am going to write here, that value is equal to 1 upon 4 pi epsilon naught time Q square divided by L square. This is the force acting on the minus Q at the center. Or second case, a simple pendulum consists of a small sphere of mass M suspended by a thread of length L. The sphere carries a positive charge Q. The pendulum is placed in a uniform electric field of strength E directed vertically downwards. Find the period of oscillation of the pendulum due to the electrostatic force acting on the sphere, neglecting the effect of the gravitational force. Okay, we'll see according to this, we'll see the diagram. Here, this is simple diagram. Okay. The people acting the positive charge Q, it is there here. The positive charge Q at an angle of deflection is equal to 5. Okay. Then this is the Q is equal to E sine 5 and this angle is equal to 5 here. Okay. This is the Q and this is equal to QE and this is QE cos 5. Okay. Now we will see the equation. Okay. We know that FR is equal to minus QE sine 5. That is FR is equal to minus QE times sine 5. Okay. Then we also know that MA is equal to minus QE sine 5. Okay. Then phi is very small. Where phi is very small, then MA is equal to minus Q E times phi. Then M is equal to M times d square x divided by with respect to dt square, okay, which is equal to minus Q times E x upon 1. Then d square x by dt square is equal to minus Q into E by M times x by 1. Okay. Comparing with the equation of linear simple harmonic motion, then we have d square x divided by dt square is equal to minus omega square x, where omega is equal to the under root of QE divided by ML. Then T is equal to pi divided by omega. Then we can write this one as 2 times pi. Omega, it is in the inverse, that is under root of ml divided by qa. This is the period of oscillation of the pendulum due to the electrostatic force.